Good morning, children. So welcome back to the online session of a mathematics class. So we are discussing about the lesson of circles. So in the last video we have studied about number of tangents from a point on a circle. So how many tangents I can write? So if I am having a point, that tangent has to pass through that point, and it has to be a tangent to the circle also. So what will be the condition for the tangent? If it is a line is called as a tangent to a circle if it intersects the circle at only one point. That means the common point between the circle and the line has to be only one exact point, exactly one common point between the circle and the line. Okay, so they know it is called as a tangent. So if it is intersects at 2 points, then it is called as a secant, not a tangent. Okay. Now, if the point lies inside the circle, so then there will be no tangent. So there is no tangent because if the point lies inside the circle, so I can't able to write the tangent. So if the point lies outside the circle, if the point lies outside the circle, suppose I am having a circle, so this is a circle center O. If the point lies inside the circle, then I can't able to write the tangent, because if I write the line which passes through this point, then that line will intersect the circle at 2 points. So therefore this line will not become a tangent, it will become a secant. So this is not a tangent. So there is no tangent that will pass through a point if the point lies inside the circle. So if the point lies on the circle, that means on the circle, on the boundary of the circle, then how many tangents I can able to write? I can able to write only one tangent which will pass through that common point. So this is the tangent. So I can't able to write one more tangent. If I write like this, then that will intersect the circle at 2 points. So that then will not become a tangent, it will become a secant. So there will be only one tangent if the point lies on the circle. So if the point lies outside the circle, if the point lies outside the circle, say suppose this is a circle. Okay, if the point lies outside the circle, so how many tangents I can able to write? I can able to write maximum 2 tangents I can able to write. So this is the point P, this is Q, point of contact, this is R. So PQ and PR are the 2 tangents I can able to write if the point lies outside the circle. Okay. So and one more point we have studied in the earlier class, that is the tangent and the radius to the point of contact both will be perpendicular to each other. That is the theorem 1 we have studied, which is very important. So the radius to the point of contact and the tangent are both perpendicular to each other. That means angle between those two will become 90 degrees. Right? So that is also we have studied. So now we will go for next concept, that is theorem 2, which is talking about the length of the tangents. Let us make theorem 2 there. Okay. So the theorem 2 is the length of tangents, the length of tangents, the lengths of tangents drawn from external point, the length of tangents drawn from external point to a circle are equal. So the lengths of tangents drawn from external point to a circle are equal. So this is the theorem 2. It is also very important theorem. Usually they will ask for 3 marks question either this theorem or theorem 1, that is tangent and radius to the point of contact, both will be perpendicular to each other. So either that theorem or this one, lengths of tangents drawn from external point to a circle are equal. So they may ask this theorem also. So for 3 marks. Okay. So we will prove this theorem. So the lengths of tangents drawn from the external point. So there will be a circle and there will be external point. If there is an external point, the point lies outside the circle. That is external point. External point means the point lies outside the circle. So how many tangents I can have? Maximum. So there will be a maximum 2 tangents I can able to write. Okay. So I am having a tangent. I am having a circle. Okay. Center O. I am having the external point. Let me get it as P. So there will be 2 tangents. These are the okay. So this will be the point of contact. This is point P. Make it as Q. And this is R. And this is point P. And this is center O. Okay. So we have defined length of the tangent also. What is the length of tangent? In the last video we have defined the length of tangent also. What do you mean by length of tangent? The distance between the external point to the point of contact. The point of contact of the circle will be called as the length of the tangent. So this will be the tangent. What is the length of the tangent? The distance between the point of contact and the external point is called as the length of tangent. So PQ will be the length of tangent and PR will be the length of tangent. We need to prove that length of tangents drawn from external point to a circle are equal. So we need to prove that PQ is one tangent, that means length of one tangent. PR is length of another tangent. I need to prove that PQ is equal to PR. I need to prove this. So according to this theorem, right? So we will define the circle first. So we are given a circle. So we define that we are given a circle with center O. We are given a circle we are given a circle with center O. So we are given a circle with center O on a point. P lying outside the circle. What they are written there, we will define that. Okay. So we are given a circle with center O and a point P lying outside the circle. So that we have defined. Okay. So point P lying outside the circle and the 2 tangents and the 2 tangents. What are the 2 tangents? PQ and PR. PQ and PR are the 2 tangents. PQ and PR are the 2 tangents on the circle from P. On the circle from P. So we need to write the 2 tangents. Okay, from the point P on the circle from the point P. So that is what we have written here. Okay. So from the point P, we are required to prove that. We have to prove that. So we have to prove that. What we need to prove? We have to prove that PQ is equal to PR will be the length of this tangent. We need to prove that lengths are equal. Okay. So to prove this, we need to do that. Okay. For this, what we need to do for this, join OP. Join OP. We need to join O and P. Let me join O and P. OQ and OR. So we need to join this. Okay. So you need to write a circle by using the compass and scale, as well as the standards also you should write by using the scale only. Okay. So join OP, OQ and OR. Okay, join. Then now you can observe that we have already learned that tangent and then radius to the point of contact will be perpendicular to each other. That means angle between those two will be 90 degree. That means this angle is 90 degree. This is also 90 degree. Clear? Because we have learned from the theorem 1 that tangents and radius to the point of contact both will be perpendicular to each other. Now PQ will be the tangent and OQ will be the radius. So both will be perpendicular to each other. That means this angle must be 90 degree, correct? So what is that angle? OQP. And we have PR is also one more tangent. OR is radius. That means OR is perpendicular to PR. That means this angle is 90 degree, right? So what is this angle? OQP. This is OQP. Representation of this angle is OQP. This is ORP. So then angle OQP and angle ORP are right angles. Then angle OQP and ORP are right angles. The reason is because these are angles between, because these two are the angles between, these are angles between radii and tangents. Radii and tangents. Clear? So why OQP and ORP are right angles? Because these are angles between radii and tangents. Because these are angles between tangents and radii. From the theorem 1, we know that angles between radii and tangent will be 90 degree right angles. Okay, perpendicular to each other. These three are same. Right angles perpendicular to each other, 90 degree. All these three terms are same. Okay, so because these are angles between radii and tangents, so that is done. So now in triangles OQP, now in triangles now we will take two triangles. We have OQP and then ORP. We will take two triangles OQP and in triangles OQP and triangle ORP. We will take these two triangles. OQP is one right triangle and ORP is another right angle triangle. Now in triangle OQP and ORP, okay, we know that okay. So now in triangle OQP and then ORP, we know that OQ is equal to OR. Why? Because OQ is also radius, OR is also radius of the same circle. Radius must be same, right? So OQ must be equal to OR. OQ must be equal to OR. The reason is radii. Radii of same circle. Radii of same circle. OQ is equal and then OP is equal to OP. OP is equal to OP. Come. OP must be equal to OP. This we need to prove. That means PQ is equal to PR by using the congruence property. Right? We have learned in class 9 also triangles. Right? Congruence of triangles. Right? So OQ is equal to R. That is the area of same circle. OQ is also radius and OR is also radius. So therefore OQ is equal to OR. Then OP is equal to OP. OP is equal to OP because common. It's a common. OP must be equal to OP. If you take any quantity, that quantity must be equal to that same quantity, right? So OP is equal to OP, and we have one more point. What is that? Angle OQP is equal to angle ORP. Correct? Proved earlier. You have written that, right? Why? The reason is both are right angles, right? Both are right angle triangle. Right. So we have three properties. So it is a right angle triangle. It is a right angle triangle. Hypotenuse side and then the other side are equal. So therefore, triangle OQP must be congruent to triangle ORP. From the RHS rule. What RHS rule says that? Both should be right angle triangle. Both should be right angle triangle. Of course, OQP and ORP are right angle triangle. Clear. Hypotenuse side must be equal. What is the hypotenuse side? OP. OP is hypotenuse side for both the triangles. OP is equal to OP. OP is equal to OP because it is a common. Then one more side will be equal to that. One more side, that is OQ is equal to OR. OQ is equal to OR. That is the area of same circle. That is also equal. Therefore, these two triangles must be congruent. These triangles must be congruent by RHS rule. Okay. So if these two triangles are congruent, then corresponding parts must be equal. So what we need to prove? PQ is equal to PR. So PQ is equal to PR. So P equivalent to P. Okay. P equivalent to P. Then Q equivalent to R. So Q equivalent to R. PQ is equal to PR. This is by CP corresponding parts of congruent triangles. These things you have learned in your class 9 also, right? Proving two triangles as a congruent, writing these corresponding parts, right? So PQ is equal to PR, that is by CP. So we have proved that PQ is equal to PR by using the congruence property of triangles. So PQ is equal to PR. This implies that. So that's it. PQ is equal to PR. This is proved. That's very simple. First, we need to define the circle. So we are given the circle with center O, and then we should define the point, a point P which lies outside the circle. Okay. So after defining this, so we need to prove that PQ is equal to PR. Statement by statement. I mean by equations, we need to prove that PQ is equal to PR. By statement, we are given lengths of tangents drawn from external point to a circle are equal. So they are given in a statement that we need to convert into a geometrical figure. Then after converting into a geometrical figure, we should write in the statement, mathematical statement. Clear? Then, so for that, we need to do that. We need to join OP, OQ, then OR. Okay? So after joining OP, OQ and OR, we need to put the PQ is equal to PR. Then we will come to know that angle OQP and then ORP are right angles. Why it is right angles? From the theorem 1, we know that tangent and the angle between tangent and the radii are 90 degrees, that is perpendicular, right? So therefore this angle, these two angles must be a right angles. Okay, so that we can take. So after that, what we will take? We will take these two triangles, in triangle OQP and then ORP. OQ is equal to OR because those two are the radius of the same circle. Then OP is equal to OP, which is common side. Then we know that this is a right angle triangle, right? Both are right angle triangle, that means angles are also equal 90 degree, right? So therefore, these two triangles are congruent. That means those two triangles are congruent by the RHS rule, then we can write by simplicity, we can write PQ is equal to PR, which we need to prove. That is prove. Okay. So this is about the second theorem, which is very easy. So this we can ask for famous question. So this is very, very important. So these theorems you need to write and practice. Okay. So you need to write twice, thrice, then you should practice that. So in the next video, I'm going to solve exercise 4.1. So before that, what you need to do that, you should go for page number 100 and we have some examples, example 1, 2, 3. So which is there in the textbook itself. So you can go through those examples, solve those examples, and you should come tomorrow with the those examples in the class work. Okay, so those has to be there in the class work. After that, we will go for the exercise 4.1, then we will solve exercise 4.2. So these two theorems are the very important theorems. With this, they may ask example 1, 2, 3 also. So therefore, you should practice example 1, 2, 3 also. If you have any doubts on example 1, 2, 3, which is very, very easy only, you can go through that. If you have any doubts in that, you just get back to me, we will solve that. Okay, so thank you.